Today our lecture is about thermal energy to electricity conversion. The contents. Introduction. Thermoelectric effect. Thermoelectric generators. Cogeneration systems. Energy conversion. Applications in thermal energy conversion. Conclusion. Thermal energy to electricity conversion is a process that involves transforming heat energy into electrical energy. This conversion is based on the principles of thermoelectricity and is widely used in various applications. The conversion of thermal energy to electricity is achieved through the use of thermoelectric materials, which exhibit the thermoelectric effect. This effect is the phenomenon of generating an electric voltage when there is a temperature difference across a material. The thermoelectric effect is the conversion of temperature differences into electricity. It is based on two main phenomena, the Seebeck effect and the Peltier effect. The Seebeck effect refers to the generation of an electric current or voltage when a temperature gradient is applied across a thermoelectric material. This effect occurs due to the difference in electron energy levels at different temperatures, resulting in the movement of charge carriers and the creation of a voltage. The Seebeck effect is the basis for thermoelectric power generation, where temperature differences are utilized to produce electricity. The Peltier effect is the reverse of the Seebeck effect. It refers to the generation or absorption of heat when an electric current is passed through a thermoelectric material. When an electric current flows through the material, it causes the transfer of heat from one side to the other, resulting in either heating or cooling of the material. The Peltier effect is utilized in thermoelectric cooling devices, such as refrigerators and air conditioners, where electricity is used to create a temperature difference. Thermoelectric generators, TGs, are devices that convert heat into electricity using the thermoelectric effect. They are based on the principle of thermoelectricity, which is the direct conversion of temperature differences into electrical voltage. TGs consist of thermoelectric materials that generate a voltage when there is a temperature gradient across them. The working principle of a TEG involves the Seebeck effect, which states that when there is a temperature difference between two different materials, an electric potential difference is created. This potential difference can be harnessed to generate electricity. TEGs can operate using various heat sources, including waste heat from industrial processes, combustion engines, and solar energy. The efficiency of TEGs is determined by the thermoelectric properties of the materials used, such as the Seebeck coefficient, electrical conductivity, and thermal conductivity. Higher efficiency TEGs can convert a larger percentage of the heat input into electricity. TEGs have a wide range of applications, including power generation in space. TEGs are used in space missions to generate power from the heat produced by radioactive decay in radioisotope thermoelectric generators, RTGs. These RTGs provide a reliable and long-lasting power source for spacecraft and satellites operating in deep space or other environments where solar panels are not feasible. Waste heat recovery. TEGs are used in industrial applications to recover waste heat and convert it into electricity. This helps improve overall energy efficiency and reduce greenhouse gas emissions. TEGs can be integrated into various systems, such as exhaust pipes, furnaces, and power plants, to capture and utilize waste heat. Thermal power plants are facilities that generate electricity by converting thermal energy into mechanical energy and then into electrical energy. These plants play a crucial role in meeting the world's electricity demand. There are several types of thermal power plants, including coal-fired power plants, natural gas power plants, oil-fired power plants, geothermal power plants, biomass power plants. Each type of thermal power plant has its own unique characteristics and fuel source. The operation of a thermal power plant involves several key steps. Fuel combustion: the fuel, such as coal or natural gas, is burned to produce heat. Heat conversion: the heat energy is used to convert water into steam. Steam turbine: the high-pressure steam drives a turbine, converting the thermal energy into mechanical energy. Generator: The mechanical energy is then used to rotate a generator, producing electrical energy. Transmission. The electricity generated is transmitted through power lines to homes, businesses, and industries. This process allows thermal power plants to provide a reliable and efficient source of electricity. Geothermal energy is a renewable source of thermal energy that can be converted into electricity. Geothermal energy is harnessed by tapping into the Earth's heat stored in the form of hot water and steam beneath the Earth's surface. This heat can be used to generate electricity through a process called geothermal energy conversion. Geothermal energy has various applications, including electricity generation. Geothermal power plants convert geothermal energy into electricity by using the heat from the Earth's core to generate steam that drives turbines. Heating and cooling. Geothermal heat pumps utilize the stable temperature of the Earth to provide heating and cooling for residential and commercial buildings. Direct use. Geothermal energy can be directly used for various purposes, such as heating greenhouses, drying crops, and spa treatments. Solar thermal power plants harness the energy from the sun to generate electricity. By concentrating solar energy, these power plants can produce high-temperature heat, which is then used to power turbines and generate electricity. This renewable energy source offers a sustainable and environmentally friendly solution for meeting our energy needs. Solar thermal power generation involves the following principles. 1. Concentrated solar energy. Solar thermal power plants use mirrors or lenses to concentrate sunlight onto a receiver, which absorbs the solar energy and converts it into heat. 2. Heat transfer. The heat absorbed by the receiver is transferred to a working fluid, such as oil or molten salt, which circulates through the system. 3. Power generation. The high-temperature heat is used to generate steam, which drives a turbine connected to a generator, producing electricity. Solar thermal power has various applications, including 1. Utility-scale power generation. Solar thermal power plants can be built on a large scale to generate electricity for the grid. These power plants can provide a reliable and renewable source of energy. 2. Industrial processes. Solar thermal energy can be used in industrial processes that require high-temperature heat, such as manufacturing and chemical production. 3. Desalination. Solar thermal power can be utilized for desalination, where the heat is used to evaporate and condense seawater, producing fresh water. Waste heat recovery systems capture and utilize waste heat from industrial processes to generate electricity. The principles behind waste heat recovery involve the following steps. Identifying the sources of waste heat. Capturing and transferring the waste heat to a heat recovery system. Converting the waste heat into usable energy, typically through the use of a heat exchanger and a power generation system. Waste heat recovery systems have a wide range of applications across various industries. Some common applications include power generation. Waste heat from power plants, industrial processes, and engines can be used to generate additional electricity. Heating and cooling. Waste heat can be utilized for heating or cooling purposes in buildings and industrial facilities. Water desalination. Waste heat can be used to power desalination processes, converting seawater into fresh water. Cogeneration systems, also known as combined heat and power (CHP) systems, simultaneously generate electricity and useful heat from a single energy source. Cogeneration systems operate on the principle of utilizing waste heat that is generated during the production of electricity. Instead of allowing this waste heat to be lost, it is captured and used for various heating applications, such as space heating, water heating, or industrial processes. This dual use of energy significantly improves the overall efficiency of the system, as compared to separate generation of electricity and heat. Cogeneration systems have a wide range of applications across various industries and sectors. Some common applications include industrial processes. Cogeneration systems are commonly used in industries that require both electricity and heat, such as chemical manufacturing, food processing, and paper production. The waste heat generated during electricity production can be utilized for various industrial processes, reducing the overall energy consumption and costs. District heating. Cogeneration systems can be integrated into district heating networks, where the waste heat is distributed to residential and commercial buildings for space heating and water heating. This reduces the reliance on traditional heating systems and improves energy efficiency. Hospitals and universities. Cogeneration systems are commonly used in hospitals and universities, where there is a high demand for both electricity and heat. The waste heat can be used for heating the buildings, hot water supply, and other thermal applications, while the electricity generated can power the facilities. Greenhouses. Cogeneration systems are used in greenhouses to provide both electricity and heat for optimal plant growth. The waste heat can be utilized to maintain the required temperature and humidity levels, while the electricity powers the greenhouse operations. Thermoelectric materials play a crucial role in thermoelectric devices, which convert heat into electricity. These materials possess specific properties and characteristics that make them suitable for this application. The selection of thermoelectric materials is based on several criteria. Thermoelectric materials possess the following properties and characteristics. Thermoelectric materials should have a high thermoelectric efficiency, which is a measure of their ability to convert heat into electricity. Materials with high thermoelectric efficiency can generate more electricity from the same amount of heat. Thermoelectric materials should have low thermal conductivity, which reduces heat loss and improves the efficiency of heat to electricity conversion. Low thermal conductivity helps to maintain a temperature gradient across the material, allowing for efficient thermoelectric power generation. Thermoelectric materials should have a high Seebeck coefficient, which is a measure of their ability to generate an electric voltage in response to a temperature difference. A high Seebeck coefficient allows for efficient conversion of heat into electricity. Thermophotovoltaic systems are designed to convert thermal radiation directly into electricity using photovoltaic cells. The principles behind this energy conversion process involve the following steps. Thermal radiation is emitted from a high-temperature heat source. The thermal radiation is selectively absorbed by a semiconductor material in the photovoltaic cell. The absorbed radiation generates electron-hole pairs, creating a voltage across the cell. The voltage is collected and converted into usable electrical power. Thermochemical energy conversion is a process that utilizes chemical reactions to convert thermal energy into electricity. It involves the use of specific chemical reactions to harness the energy released during the reaction and convert it into a usable form of energy. Thermochemical energy conversion operates on the principle of utilizing the heat generated by chemical reactions to produce electricity. This process involves two main steps. Heat input. A high-temperature heat source is required to initiate the chemical reaction. This heat can be provided by various sources such as concentrated solar energy, combustion, or waste heat from industrial processes. Chemical reaction. The heat input triggers a chemical reaction that results in the release of energy. This energy is then harnessed and converted into electricity using various methods such as thermoelectric generators or fuel cells. Thermochemical energy conversion has a wide range of applications in different industries and sectors. Some common applications include: thermochemical energy conversion can be used in concentrated solar power systems to convert solar energy into electricity. This technology utilizes high-temperature heat from concentrated solar energy to drive chemical reactions and produce electricity. Thermochemical energy conversion can be employed to recover waste heat from industrial processes and convert it into electricity. This helps in improving overall energy efficiency and reducing energy wastage. The heat generated by chemical reactions in fuel cells is harnessed to produce electricity, making fuel cells an efficient and clean energy source. Thermionic energy conversion is based on the emission and collection of electrons from a heated cathode. When a cathode is heated to a high temperature, it emits electrons due to thermionic emission. These electrons are then collected by an anode, creating an electric current. The key principles of thermionic energy conversion include thermionic emission, the process by which electrons are emitted from a heated cathode. Electron collection, the collection of emitted electrons by an anode, creating an electric current. Temperature gradient, the temperature difference between the cathode and the anode, which drives the thermionic emission and electron collection processes. Thermionic energy conversion has various applications in the field of energy conversion and power generation. Some of the key applications include thermal power generation. Thermionic energy conversion can be used to convert heat energy from various sources, such as fossil fuels or nuclear reactors, into electricity. Space exploration. Thermionic energy conversion is used in space probes and satellites to generate power from the heat produced by radioactive decay. Industrial processes. Thermionic energy conversion can be utilized in various industrial processes that require the conversion of heat into electricity. Thermomagnetic energy conversion is a process that utilizes the magnetic properties of materials to generate electric voltage in the presence of temperature gradients. This phenomenon, known as the thermomagnetic effect, is based on the principle that a magnetic field can be induced or modulated by temperature changes. The principles of thermomagnetic energy conversion involve the use of materials with temperature-dependent magnetic properties, such as ferromagnetic or paramagnetic materials. When a temperature gradient is applied across a thermomagnetic material, it induces a magnetic field due to the difference in thermal energy. This magnetic field can then be used to generate electric voltage through various mechanisms, such as magnetic induction or the Hall effect. Thermomagnetic energy conversion has several applications in the field of renewable energy and waste heat recovery. Some of the key applications include thermal energy harvesting. Thermomagnetic energy conversion can be used to convert waste heat from industrial processes or power plants into electricity, improving overall energy efficiency. Thermal sensors. The thermomagnetic effect can be utilized in the development of thermal sensors for temperature monitoring and control in various industries, such as automotive, aerospace, and manufacturing. Thermal imaging. Thermomagnetic energy conversion can be employed in thermal imaging devices to detect and visualize temperature variations in objects or environments. Thermophotonic energy conversion is a process that utilizes photons to generate electricity. It involves the conversion of thermal energy into light, followed by the conversion of light into electricity. This technology is based on the principles of thermophotovoltaics, TPV, and is a promising solution for efficient energy conversion. Thermophotonic energy conversion has a wide range of applications in various industries. Some of the key applications include solar energy conversion. Thermophotonic systems can enhance the efficiency of solar cells by converting a broader spectrum of sunlight into electricity. Waste heat recovery. Thermophotonic devices can be used to capture and convert waste heat from industrial processes into electricity, improving energy efficiency. Portable power generation. Thermophotonic energy conversion can be applied in portable devices, such as wearable electronics and remote sensors, to provide self-sustaining power sources. Thermoelectric energy conversion is a process that utilizes the Seebeck effect and the Peltier effect to convert thermal energy into electricity. Seebeck effect. The Seebeck effect is the phenomenon where a temperature difference across a thermoelectric material creates an electric voltage. This effect is based on the principle that when two dissimilar conductors are connected in a closed circuit, an electric current is generated due to the difference in temperature between the two conductors. Peltier effect. The Peltier effect is the phenomenon where an electric current flowing through a thermoelectric material creates a temperature difference. This effect is based on the principle that when an electric current passes through a junction of two dissimilar conductors, heat is either absorbed or released at the junction, depending on the direction of the current. Applications of thermoelectric energy conversion. Waste heat recovery. Thermoelectric energy conversion can be used to recover waste heat from industrial processes and convert it into electricity, improving energy efficiency and reducing environmental impact. Power generation in remote locations. Thermoelectric generators can be used to generate electricity in remote locations where traditional power sources are not available or feasible, such as in space missions or remote monitoring systems. Thermal management. Thermoelectric coolers can be used for precise temperature control in electronic devices, such as in computer processors, to prevent overheating and improve performance. Thermionic energy conversion relies on the following principles. Thermionic emission is the process of electrons being emitted from a heated cathode. When the cathode is heated to a high temperature, electrons gain enough energy to overcome the electrostatic forces holding them in the metal lattice. These emitted electrons are known as thermions. Once the thermions are emitted from the cathode, they are collected by an anode. The anode is typically at a lower temperature than the cathode, creating a temperature gradient that helps in the collection of the electrons. The collected electrons can then be used to generate electricity. Thermionic energy conversion has various applications in different fields. Space exploration. Thermionic energy conversion has been used in space exploration missions to generate electricity from the heat produced by radioactive materials. This technology provides a reliable and efficient power source for spacecraft and satellites in remote locations. Waste heat recovery. Thermionic energy conversion can be used to recover waste heat from industrial processes and convert it into electricity. This technology helps in improving energy efficiency and reducing the environmental impact of industrial operations. Thermophotovoltaic energy conversion is a process that utilizes photons to generate electricity through the use of photovoltaic cells. Thermophotovoltaic energy conversion operates on the principle of converting thermal radiation into electricity. It involves the following steps. Thermal source, a high-temperature heat source is used to generate thermal radiation. Selective emitter, a selective emitter is used to control the spectral properties of the thermal radiation, allowing only certain wavelengths to pass through. Photovoltaic cells are used to convert the absorbed photons into electricity. Thermophotovoltaic energy conversion has several applications in various fields, including solar power. Thermophotovoltaic systems can be used to convert solar radiation into electricity, providing an alternative to traditional solar panels. Waste heat recovery. Thermophotovoltaic systems can be used to recover waste heat from industrial processes and convert it into usable electricity. Space exploration. Thermophotovoltaic systems can be utilized in space missions to convert the thermal radiation emitted by spacecraft into electricity. Thermomagnetic energy conversion is a process that harnesses the magnetic properties of materials to generate electric voltage in the presence of temperature gradients. This phenomenon, known as the thermomagnetic effect, has been studied extensively for its potential applications in energy conversion and power generation. The principles of thermomagnetic energy conversion are based on the following key concepts. Magnetic properties of materials. Certain materials, such as ferromagnetic or paramagnetic materials, exhibit magnetic properties that can be influenced by temperature. When subjected to a temperature gradient, these materials experience changes in their magnetic properties, leading to the generation of an electric voltage. Temperature gradients. Thermomagnetic energy conversion relies on the presence of temperature gradients, which are differences in temperature across a material or system. These temperature gradients create an imbalance in the magnetic properties of the material, resulting in the generation of an electric voltage. Power generation. Thermomagnetic energy conversion can be utilized to generate electric power. By creating and controlling temperature gradients in a thermomagnetic device, an electric voltage can be induced, which can then be harnessed to power electronic devices or be integrated into larger energy systems. The principles of thermomagnetic energy conversion have found various applications in different fields. Some notable applications include waste heat recovery. Thermomagnetic energy conversion can be used to recover waste heat from industrial processes or power generation systems. By converting the temperature gradients in waste heat streams into electric power, thermomagnetic devices can improve overall energy efficiency and reduce environmental impact. Renewable energy harvesting. Thermomagnetic energy conversion can also be utilized in renewable energy systems, such as solar or geothermal power. By capturing temperature gradients in these systems, thermomagnetic devices can enhance power generation and improve overall energy efficiency. Portable power generation. Thermomagnetic energy conversion has the potential to enable portable power generation. By integrating thermomagnetic devices into small-scale systems, such as wearable electronics or remote sensors, electric power can be generated from temperature gradients in the surrounding environment. Thermal energy conversion efficiency is a measure of how effectively thermal energy is converted into electricity. There are several factors that affect the thermal energy conversion efficiency, including temperature difference. The greater the temperature difference between the heat source and the cold sink, the higher the efficiency. Thermal conductivity. Materials with higher thermal conductivity can transfer heat more efficiently, leading to higher conversion efficiency. Heat losses. Minimizing heat losses during the conversion process can improve efficiency. To improve thermal energy conversion efficiency, several methods can be employed. Optimizing heat exchangers. Designing efficient heat exchangers can enhance heat transfer and reduce losses. Using advanced materials. Utilizing materials with high thermal conductivity and low thermal resistance can improve efficiency. Implementing thermal insulation. Insulating the system can minimize heat losses and improve overall efficiency. Thermal energy storage systems play a crucial role in improving the efficiency and flexibility of thermal energy conversion. These systems store thermal energy for later use, allowing for better management and utilization of heat energy. Thermal energy storage systems operate based on the principles of storing and releasing heat energy. These systems can use various methods to store thermal energy, including thermal energy storage systems find applications in various industries and sectors, including sensible heat storage. This method involves storing heat energy by increasing the temperature of a storage medium, such as water or rocks. Latent heat storage. In this method, heat energy is stored by changing the phase of a material, such as from solid to liquid or liquid to gas, while maintaining a constant temperature. Thermochemical storage. This approach involves storing heat energy through chemical reactions that absorb and release heat. Renewable energy integration. Thermal energy storage can be used to store excess heat generated from renewable energy sources, such as solar or geothermal energy, for later use when the demand is high. Industrial processes. Thermal energy storage systems are utilized in industries to store and release heat energy during various manufacturing processes, improving energy efficiency and reducing costs. Building heating and cooling. Thermal energy storage can be used in buildings to store excess heat or coolness during off-peak hours and release it when needed, reducing energy consumption and optimizing HVAC systems. Nuclear power plants generate electricity by harnessing the thermal energy released from nuclear reactions. These reactions produce heat, which is used to produce steam. The steam then drives a turbine connected to a generator, generating electricity. Coal power plants are one of the most common applications of thermal energy to electricity conversion. They use coal as a fuel source to generate heat, which is then used to produce steam. The steam drives a turbine connected to a generator, producing electricity. Wind turbines convert the kinetic energy of wind into mechanical power, which is then converted into electricity. Wind power is a clean and renewable source of energy and is commonly used in wind farms. Geothermal power plants harness the heat from the Earth's core to generate electricity. This is done by extracting hot water or steam from underground reservoirs and using it to power turbines. Geothermal energy is a reliable and sustainable source of power. Waste heat recovery is widely used in various industrial processes to capture and convert thermal energy into electricity. Industries such as steel, cement, and chemical plants generate large amounts of waste heat during their operations. By utilizing thermal energy conversion technologies, this waste heat can be harnessed to generate electricity, reducing energy costs and environmental impact. Waste heat recovery systems are also used in power generation facilities to maximize energy efficiency. In conventional power plants, a significant amount of heat is lost during the electricity generation process. By implementing thermal energy conversion technologies, such as organic Rankine cycle (ORC) or Kalina cycle systems, this waste heat can be converted into additional electricity, increasing the overall power output of the plant. Waste heat recovery technologies are being explored and implemented in the automotive industry to improve fuel efficiency and reduce emissions. In vehicles, a significant amount of energy is lost as waste heat through the exhaust and engine cooling systems. By using thermoelectric generators or turbochargers with integrated waste heat recovery systems, this waste heat can be converted into electricity, which can be used to power various vehicle systems or recharge the battery. Cogeneration systems utilize thermal energy to electricity conversion technologies in various applications. Industrial applications. Cogeneration systems are commonly used in manufacturing plants, where waste heat from industrial processes is converted into electricity. Commercial applications. Cogeneration systems are implemented in commercial buildings such as hospitals and universities to provide electricity and heat for various facilities. Residential applications. Cogeneration systems can be used in residential buildings to generate electricity and heat for households, increasing energy efficiency and reducing reliance on the grid. In conclusion, the process of converting thermal energy into electricity is of utmost importance in various industries. It involves utilizing a heat engine to convert the thermal energy into both mechanical and electrical energy. This conversion process holds great significance and is widely applied in a multitude of industries. Its applications span across a diverse range of sectors and continue to evolve as technology advances. Thus, the conversion of thermal energy to electricity is becoming increasingly indispensable in modern industrial practices. Thanks. You can find a link below in the description to download a free copy of the presentation. The link takes you directly to Google Drive. Please like, subscribe and write a comment. Please don't sell the presentation or upload the file to another websites, because it's copyrighted. So what is the next video? Write down in the comments section the topic of the presentation and the number of slides. See you in the next video. Presentations upon your request.